Let us tackle some of the problems in the tutorial. So we'll look at answering question 1. Question 2 will skip, but it's similar to question 3, so we'll answer question 3 in this session. And then we'll tackle question 5, 6, 7. Question 4 is similar to question 5, so if you have any issues with question 4, you just look at the solution for question 5. And then question 8 is as given in the lecture slides, as well as question 9. Question 10 is also given in the lecture slide, lecture 1.2.2. Question 11 is the question from the text. So take some time to look at the text, the reference text, that is the reference book. And then we'll tackle 12, 13, 14, 15. And 16, we'll leave it for you. You'll do it independently, so it's very similar to question 7. And then we'll look at question 17. So the first question 1. So question 1 says, briefly describe the following typical control system elements. An actuator that converts electrical to mechanical energy. So the most obvious one, in this case, the most obvious actuator would be an electric motor. And our description is an electric motor that turns its shaft when powered by an electrical current. The motor converts input electrical energy into motion. So here, because the question says, briefly describe, so you have to be careful to make a description. And in your description, obviously, you have to explain what is, how it converts, what type of electrical energy it takes in, and then what type of mechanical energy it produces. So you see here we say an electric motor. That's first we state the question. The answer, and then we say it turns its shaft when powered by an electrical current. So the motor converts the input electrical energy in the form of current into motion, which is the mechanical energy. So that's what you need to take note of. Now, the second question, question 1a, is a sensor that can be used. It says a sensor that can be used to detect temperature. And in this example, so there are many, of course. These are not definitive answers. You can pick any other answer which comes to mind, but you just need to give it a description that fits the question that you have. So you need a sensor here that detects temperature. So obviously, sensors that detect temperature, the ones that are common, it's a thermocapsule or a thermometer. And so here I say a mercury thermometer with a calibrated scale whereby the mercury expands in proportion to the level of temperature it is exposed to. So here I give you the description of how it detects the temperature using the expansion of mercury. So you could say, obviously, say for example, you take a bimetallic strip. The bimetallic strip is a strip of two metals which bends upon detection of a certain threshold temperature. So you can also fill in that. You can also put a thermocapsule and explain how the thermocapsule operates. So that will also suffice. And then the second one here is, you briefly describe an error signal in a room heating system that uses a thermostat. So in a room heating system that uses a thermostat, so the idea is you have a room and then you have an air conditioner, and then the air conditioner, you set it to a certain temperature on the dial. So if you set, say, a certain set point TS, and then the room, it's also, let's say it's a cold day, the room it's at temperature TR. So what would be the error signal? So in a control system, the aircon will be on for as long as the temperature of the room is bigger than the temperature of the set point is bigger than the temperature in the room. So this becomes the error signal that makes sure that the air conditioner is on. So here I'm saying the error signal is the temperature difference between the set point, TS, and on the thermostat and the temperature of air within the room. So that is an error. There could be, that's an error. That's an error signal that you will have in your control system. And then for these, the question is a sensor used to detect how fast a car is moving. And for this, we say an analog speedometer. An analog speedometer is my answer, whereby the dial deflects. So the speedometer, which will show the different speeds of the car. So the dial will turn based on how fast the car is moving. So whereby the dial deflects more and more as the speed of the car increases. So if the question says here, I think the idea here is if the question says briefly describe, you should be able to tackle it because your answer has to be a description. You can't just list you can't just state the answer. You can't just say speedometer, for instance, or you just say electric motor. You have to describe how this element works. So take note of these keywords in the question. Before we tackle question 3, I'd like us to look at the different elements of a typical control systems or feedback control system. So what you need to show actually in a typical control system, or as you are assessing a system that's been described, you need to look at the appearance of each of the following elements. So you would need first to, starting from this side, you need to look at the reference signal here, or the desired response, or sometimes referred to the reference signal. So this would be what or sometimes it's called the set point. This would be what you desire your output to be, and then from there it goes into this comparator to generate an error signal. The error signal is the difference between the desired response reference or set point and the measured output. So the controller then takes this error signal and it generates a control signal to give it to the actuator. So sometimes in the process there is a disturbance from an external environment whereby which affects the control signal, which structurally the designer of the control systems can't do anything about. It's just sometimes it's just naturally the disturbance, and this control signal then goes into an actuator which simply acts like an amplifier or a signal converter which converts from a low level input control signal to a high powered output signal, which can then be able to control the process. And then the process would then generate an output signal, and then the output signal would be sampled by a feedback sensor. So this becomes your feedback, and the sensor would detect from the output, would measure the output, but in the process of measuring there is bound to be some measurement noise in the process, and this measured output goes back to generate the error signal. So that's how basically the feedback loop operates. So in most cases you will find that so to draw a control loop you would definitely need a controller, an actuator, a process. You would, if it's a feedback, you would need definitely a sensor as well, the actual output, the reference, and the error. In some of the cases, not all, it would it would be necessary to have disturbances depending on how that described, and then you would also be able to identify the measurement noise. So when you try and analyze your control system, your feedback control system, you need to identify those different elements. And these other ones, the controller, actuator, process, output, sensor, must always be there in your analysis. So let's look at the question 3. It says and the question says, in a chemical plant shown in figure 1, a process control system is required to maintain a consistent mixture of output by blending the main steam and additive. The consistency is maintained using an infrared steam analyzer and by controlling the position of the valve on the additive stream pipe. Complete the control feedback loop and sketch a block diagram describing the operation of the control feedback loop. Now, as we have stated initially, if we need to analyze this, we said some of the important elements here which you can look at are: 1, the reference signal, and then the output signal, and the error signal, and the measurement signal, the measured signal. So these are the signals that you would have to deal with, that you need to identify. The most important control elements would be the controller itself, and then the second one would be the actuator. The other would be the process, and then the measurement element. This would be your important items to analyze. So if we look at the process as we are reading, there is a process control system that's required to maintain a consistent mixture of the output. So we see the output as a consistent mixture. So already we have identified the output is supposed to be a consistent mixture, which is here. Use a different marker for that. Right, and then we look at further the other issue, which says now, if you go on to read further, it says by blending in the main steam and additive, and then now you would think that this would then be the input. This is the input to the process, but not input to the control system. Remember, so this thing, the main steam and the additive, these are inputs to the process, but they are not inputs to the control system. So there's a difference between what the control system does and what the process does, right? So the control system runs the process, but they do not have necessarily the same input. So you have to be mindful of that issue. So the consistency is maintained using an infrared steam analyzer. So we can see that there's an element here called an infrared steam analyzer. And then we look at it here, it says infrared steam analyzer. The output of that is the measurement of composition. So already we can see we have identified that the infrared steam analyzer it acts as a measuring element because it gives you a measurement of composition, which is the measured signal. So here we have identified this as well as that. So these are the elements and the measurement. Now, moving on, we say by controlling the position of the valve. So it controls the position of the valve. So, so clearly we see the control signal here, which is the position of the valve. We see also the valve. This should be the actuator that's been controlled. And then we see that what the controller does. So the controller controls the position of the valve, and the valve itself is an actuator. And we go on. So it says to control the position of valve on the additive steam pipe. Now what we are left with after reading this question is supposed to be, now what is the process, what is the reference signal, right? So if you look at the process, obviously we already know that the process is the steam blending process that's been controlled. So implicitly that's defined in this process control system. The process is the steam blending process. And then the error signal then, okay, before we talk about the error signal, the reference signal, let me use a different marker for that. Let me use the purple marker for that. The reference signal would be what's desired. So in this case, what do you desire? It's required to maintain a consistent mixture. So the reference signal is that consistent mixture. So the consistency here, consistent mixture is what we desire as the reference signal. The error would be the difference between the reference signal and the output. So that would be our error. So let's move on then to draw a sketch of that control system to complete the loop. So now that we have analyzed, so our control system would be of the following format. So we have here the reference signal, the measurement coming from behind, and then this goes to the controller. Okay, let me cancel that. This goes to the controller. And then the controller takes it to the actuator. The actuator turns it to the process. And then within the process, we have a feedback signal. And the feedback signal goes all the way back to next to the input. So we have a measurement element here. The measurement element, just write a measurement. And so we have now explained that the input here, the main input, the reference signal, should be a consistent mixture. Consistent. The consistent mixture or consistent blend, and the output itself should be the actual mixture that you're getting. And then there's a measurement here, and the measurement is done by the infrared analyzer. Infrared analyzer. So I just put IR here for infrared. The infrared analyzer gives us the measurement composition. Measurement of composition. Now, once you've got the measurement of composition, we can then populate what the actuator is. The actuator is actually the valve, and then the process is the steam blending process. So it's the steam blending process. So we know here is the error signal. which was not explicitly stated, but the error signal would be the measurement composition. Measurement of composition, the difference between the measurement of composition and the consistent mixture that we want. And the controller could be whatever a computer, which is not clearly stipulated in the question, but there's a controller which then somehow controls the valve. This might be also manual controller, it might be a person, it might be, but it's not clearly stated, so we'll not write anything here because it's not been clearly stated. So then this completely answers the question, and it's able to cover all the aspects of the process that have been mentioned in the question. Now moving on to question 5. So in question 5, this is the question on linearization. We look at question 5, which says a spring develops a force F represented by a relationship f of x is equal to f of x is equal to x plus 1.43 x cubed. So a spring develops that type of force where x is the displacement of the spring. So in this case, the displacement of the spring it's not the linear function of the force in this case, because if it's a linear function, it was also supposed to be a constant times. If it was a linear function, then f, typically a linear springs of this structure, f times x. But in this case, x has some higher powers. So what we do in this case to make the calculation is that so the first question actually says find the value of the force for the steady state operation at the two operating points x0 and x is equal to 2. And then obtain a linearized model for both operating points and compare them. Now it says here we should find basically the value of the force when it's operating at x2 and when it's operating at x1. So now for the first one, f of 1 is equal to 1 plus 0.4 times 1 cubed, and this gives us 2.4. The second one is f of 2 is equal to, is equal to 1 plus 1.4 times 2 cubed, which is equal to 1 plus 1.4 times 8, which then gives us this. And the answer becomes 12.2. Right, now, so that's question A. Question B says, obtain a linearized model for both operating points and compare them. So we want to obtain a linearized model of this, and we know that by Taylor's expansion, if you have a function f of x, which is nonlinear, and in this case, the linearized model of the function would be f bar is equal to derivative of f around the point x evaluated at the point x0 times x bar, where the f bar is equal to the f minus f at that point, and the x bar is equal to x minus x0. So this is basically like a constant m times x bar, where m or m is actually equal to the slope, where this value m or k in this case is equal to this first derivative. So our objective then becomes deriving that first derivative. So now we take the first derivative of f of x, it's equal to x plus 1.4 x cubed over x, which is equal to 1 plus 3 times 1.4 times x squared, which is equal to what? Which is equal to 1 plus 4.2 x squared, right? So this is what your first derivative is. But now we need to have the first derivative be evaluated at x is equal to 1 for the first point. So it means, therefore, this is going to be 1 plus 4.2 times x squared, which is 1 squared, and then this gives us 5.2. The second one, we evaluate it at x is equal to 2, and this is 1 plus 0.2 times 2 squared, and that gives us 18.8 if we do the calculation. So we have obtained the linearized models then. So at x0 is equal to 1, the linear model is going to be f bar is equal to 5.2 x. At x0 is equal to 2, the linear model is going to be f bar is equal to 18.8 x bar. So this becomes our answers for the models. This becomes our answer for the linear model. Now we need to compare them. When we compare them, we see that what is the difference here? You can see that the slope here is much bigger than the slope at this point, right? I think that's what we can see. The structure of the linear model is the same. It's f times